Hello, welcome to this video. So in this video we're going to be looking at generalising the factorial and exploring why we might want to generalise the factorial. Many will have seen the factorial of an integer before. In this video we'll be looking at applications of factorials of fractions and seeing how this generalisation can be used in something known as fractional calculus, and we'll be using it to define the Riemann-Louville fractional derivative and integral, before mentioning a few applications within physics and even in biology. So I hope that there's something really in this video for everyone. I am at a different location, so if there is some background noise, just think of it as some kind of like natural relaxation or music. I think at the moment the heating system is humming, but you know, it's just added background music to the mathematics and physics. So why is the standard factorial useful? Well, that's kind of like the most important question to begin with, because the standard factorial, that is the factorial of integers, provides a pattern that we would expect any factorial function to follow, even if it could give the factorial of fractions. And so let's consider the importance of the factorial of integers to begin with, to find out these patterns. Well, the factorial is traditionally introduced when looking at how to arrange an integer number of distinct objects. So here we have three distinct pictures: an image of a dragon, an image of Gandalf or Lauren, as he is more formally known in Tolkien's lore, and an image of Aslan. And clearly these are three distinct pictures, and we might wonder, if we're going to rearrange their order, how many arrangements can we have? And it turns out that that is given by the number of distinct objects, so in this case 3, factorial. So we take the factorial of the number of distinct objects to get the number of ways we can arrange those distinct objects. If we have objects which are identical and we want the number of unique arrangements, then we still use factorials, but we use something known as the NCR function. But anyway, this is how the integer factorial, if you like, the standard factorial, is often introduced. We can also use factorials when trying to expand binomial expressions, and by binomial expressions I mean expressions involving two algebraic terms. So if you wanted to say expand this, yes, you could explicitly work out what it would be by hand, but a much quicker way is to use the binomial series, which I've shown here. And the column with nk is nck, so it's using the NCR notation. So the binomial series does use factorials ultimately. So factorials come up in a lot of places when we're looking at the, at taking the factorial of an integer. However, there is one factorial which this doesn't really explain, which a generalised factorial would, and that's 0 factorial. And then obviously this notion of factorial isn't so great if we want to understand what is a half factorial. But we can get an intuition using the top definition of factorial, the idea of it being a description of how many ways we can arrange distinct things to work out what zero factorial should be. And for this, imagine zero, how we should physically think of zero factorial. Well, if we had zero things, we essentially have a vacuum, we have empty space. So imagine a box and there is nothing in that box. Zero factorial, according to our top definitions, is how many ways we can arrange that nothingness in the box. Well, if the box contains nothing, there is only one unique arrangement of nothing. We can't do anything with the nothing to cause it to have various arrangements, various distinct arrangements, and therefore zero factorial should be one. There is only one way in which nothing can be arranged, so to speak. But because arranging nothing is a slightly strange idea, really zero factorial can be justified in other ways by extending patterns. I mean, another way to work out what zero factorial should be is if we look at x minus y to the power 10, well, we could say, okay, let's take, instead of that, let's have x minus y all to the power 0. Now we know from how powers work that x minus y all to the power 0 should be 1. And using the binomial theorem, that implies that 0 factorial should also be 1. So we can get to 0 factorial various ways. But now let's formalise the idea of n factorial, where n is an integer, to see certain patterns, and then look at the gamma function that generalises the idea of the factorial of an integer. So this slide is all about going beyond boxes. So going beyond the standard integer definition of a factorial. Well, for this, we have to understand more formally how the integer factorial comes about to spot some patterns. So if we want to work out how to arrange n distinct objects, like n distinct images, what we can do is we can think about having, say, n slots to put those n images. And then if we pick one image at random, it doesn't matter which image, there are n slots that image can go in. And then if we look at where we can put the second image, well, there are now n minus 1 slots that can go in, because we've already placed the first image in one of our n slots. So there are n minus 1 slots remaining. And we can keep doing this. And then we end up concluding that there are n factorial ways to arrange those n distinct objects. Now, I'm not going into this in too much depth, because this definition of factorial is something you are likely, you've probably seen before, seen something like that before. But what it does introduce is a very important property of factorial and the factorial function, and that is that n plus 1 factorial is equal to n factorial times n plus 1. And using the idea of 0 is describing a vacuum. You can even justify, as mentioned before, the idea that 0 factorial is 1. And that is also borne out in probability where the factorial function is used, such as defining the binomial distribution. So how can we generalize this to, the factorial of fractions? What function? And an ambulance just goes past. Well, luckily our problems are not anything dire. We just have to find the factorial of fractions. So how could we find the factorial of fractions? Slight tongue twister there. Well, we want a function which, importantly for any integer n, gives the same result as n factorial, or the factorial of something in terms of n, where n is an integer. We also want that for any n, whether n is an integer or not, n plus 1 factorial to equal n factorial times n plus 1. And we also want it to satisfy the idea that 0 factorial is 1. Now, a function that can do all those things is the gamma function. Now, strictly, the gamma function of n is n minus 1 factorial, but obviously you can use that to work out the factorial of any value n. Now, strictly because the gamma function is an integral, there is the potential for the integral to diverge, so there are restrictions on what factorials this function can give us, but it can give us the factorial of a half. In fact, it can give us any positive factorial. It also shows very neatly that 0 factorial is 1. And to get that, all one has to know is that 0 factorial would be gamma of 1. And if we put n equals 1 into our integral, we get the integral from 0 to infinity of t to the 0 e to the minus t dt, which would be equal to the integral from 0 to infinity of e to the minus t dt, because t to the 0 is just 1. And then from that point, it's just kind of, doing standard integration. So this is the gamma function that generalizes the notion of the factorial. Now, for those which are looking at that and wondering where is the symbol gamma, well, that T-like symbol with half of its top missing is the capital letter gamma. We tend to save the capital letter gamma for special cases, for special purposes in mathematics. So it's also used in Christoffel symbols. So you may have seen it before, but it is noticeably different from the lowercase gamma. So I thought, best mention, at least from a notation perspective, why we're calling this a gamma function. Now, because the gamma function generalizes the notion of a factorial, it turns out to be very useful in extending ideas of repeated integration that occur in calculus, and therefore allowing us to define things like half integrals. And therefore, ultimately, if we consider an integral as an antiderivative, allowing us indirectly to get to half derivatives. And that is all borne out in Louville Riemann fractional calculus. Now, it's worth saying that there are many ways to go about finding operators within fractional calculus. In this video, I'm just sticking to one, mainly because that one doesn't involve the calculation of limits, which certain other versions of fractional calculus operators do, and also because the Riemann-Louville operators play a role in important physical systems we will come to at the end of this video. Now, before we go on to look at the Riemann-Louville fractional integral and then the fractional derivative, it's helpful to consider, if we're thinking about fractional calculus, such as trying to get some kind of fractional derivative operator, some of the complications that are involved and why there are various forms of things like the fractional integral which produce different answers, and more generally why fractional calculus leaves much room for playing around and scope of different answers, and there is much more variety in the operators than we have in standard real or complex analysis. So let's see if we can find a rather ad hoc way to generalise the idea of a derivative. And I'm sticking with a derivative because derivatives, at least when we aren't doing fractional calculus, so derivatives in ordinary real analysis are much more straightforward than integrals. So if we have a function like e to the kx, then the nth derivative of y, which I've notated as y and then as a superscript n in brackets above the y, would be, k to the n times y. And this is just using a mixture of the chain rule and the definition of the exponential function. And if you would like to learn more about the exponential function, I'll put a link to the video on E, the Euler constant, down below in the description. But anyway, the reason I'm mentioning the derivative of e to the x is because it's fairly easy to generalise. For example, continuing the pattern we have above, the half derivative of y should be y times the square root of k, and that's just extending the pattern. So, it might look like fractional differentiation is quite straightforward. But there is a complication, and that complication becomes particularly evident if we look at using complex exponentials to work out things like the half derivatives of trigonometric functions. So let's use the generalisation of how we've taken the derivative of e to the kx to work out the partial derivative or fractional derivative. I should say, partial differentiation is different. So to find the fractional derivative of a trigonometric function. Well, we can write cos of x in terms of our complex exponentials, or in terms of complex numbers, and cos of x is just a half lots of e to the I x plus e to the minus ix, as is given by the Taylor series of the cosine function. So cos to the half of x should be this kind of second term in our bottom blue box. And then we can use kind of a symmetry with the square root of I and the square root of minus I to simplify this. And it becomes, as I encourage the viewer to attempt themselves if they want to play a little bit around with the mathematics, we get the half derivative of cos of x is e to the ix over square root of 2. Now, this all looks lovely so far. However, we are dealing with square roots, and the solution to what a square root is ambiguous. If k is positive, then the square root of k has two distinct values. If we're taking the square root of an imaginary or complex number, well, then things become way more complicated. You know, so the thing is, when it comes to kind of like generalizing differentiation, we can see that the ad hoc method, so just extending the pattern of, you know, ordinary calculus, produces a lot of ambiguity. So to get around this, we have to be more clever than just blindly extending patterns seen in ordinary calculus. And so what we're going to do is we're going to start with defining a fractional integral, because rather ironically that's much easier than defining a fractional derivative. And we'll see that by carefully choosing a version of the integral which makes use of the notion of a factorial, we can actually get to a fractional integral which is very nicely and neatly defined. So I'm now introducing the Riemann-Louville fractional integral, and this is really where the gamma function shines within physics, because physics is forever in love with calculus. I mean, without calculus, so much of physics would have been present. Physicists love, they adore calculus. So, I couldn't resist bringing some calculus into this video. So let's work out a generalization of the integral to fractional calculus. And this particular generalization is called a Riemann-Louville integral, and I like it because it doesn't involve explicitly necessarily calculating limits. I mean, there is an integral which strictly is a limit, but using clever substitutions and stuff, one doesn't often have to worry too much about how to calculate limits. So we start with Cauchy's formula for repeated, repeated integration. So in this notation, we are looking at integrating the function f n times, and that's equal to the expression on the right-hand side of the equal sign. And you'll see that this expression involves m minus 1 factorial. Now you can prove this using proof by induction, which I would encourage you to do. It's fairly easy to show, for example, that the 0th integral of f does indeed just return f, and the first integral of f returns what we would expect, just the normal integral of f, and from then on showing that if it works for n, it works for n plus 1 is a fairly straightforward process. Now we can generalise this notion of a nth order integral by just generalising the factorial, and we've seen that the generalisation of the factorial is the gamma function. So a natural way to generalise it is this, and remember n minus 1 factorial is equal to gamma of n. It's important not to get the n's confused. And this is our Riemann-Louville integral, which I think looks pretty neat. And you can use this immediately to calculate half integrals. For the purpose of this video, the Riemann-Louville integral is most useful because we know that differentiation cancels out almost integrals, or integrals are antiderivatives, and therefore integrals cancel out differentiation. So however you want to think of it, we can now use the Riemann-Louville integral in combination with the standard derivative operator to construct fractional derivatives. And it's fractional derivatives through the branch of maths which deals with fractional differential equations, which play such an important role within the landscape of physics. So we've seen the Riemann-Louville fractional integral. Let's now find the fractional derivative from it. So we start with the fractional integral, and then, as mentioned, we can use differentiation to kind of undo integration and get a fractional derivative operator. So d alpha is our fractional derivative operator. So alpha is the order of differentiation. So if alpha was 1, we would be dealing with standard first order ordinary derivatives. But if alpha is a fraction, then this is an example of a fractional calculus operator. Now, you might kind of like wonder how we've explicitly got to this. Well, essentially, like d to the alpha is kind of like, well, we are differentiating the n minus alpha integral n times, which is going to give us the minus alpha integral. But because differentiation is the reverse of integration, the minus alpha integral is the same as the alpha order derivative. That's kind of like the logic of what's going on here. But this kind of expression for the fractional derivative looks pretty bulky, so can we simplify it? And the answer is we can, because if we look at the left-hand side, we've got a derivative operator where we only need the order alpha, but on our right-hand side, we have got n appearing. Now we can pick n to be whatever we want. It doesn't affect alpha. Alpha and n are independent. We're using n because we're differentiating n times to undo integration n times. But we can pick n to be whatever we want. Now for simplicity, due to higher order derivatives being complicated and due to wanting to make the power n minus alpha minus 1 as simple as we can, we pick generally n equals 1, leaving us with this lovely expression for a alpha order derivative, where again alpha doesn't have to be an integer, alpha is now allowed to be a fraction. So we have a fractional derivative operator. Now, in operators where we have a derivative acting on an integral, we sometimes call such an operator a differintegral. So this is an example of a useful differintegral within physics. So we've now introduced the idea of a fractional derivative, but where is this useful? What kind of physical systems would we need fractional calculus and more specifically fractional derivatives for? And to explore that, we will be looking at a process known as subdiffusion, and then looking at a particular strange type of relaxation. And when I say relaxation, I don't mean we are going to, lie down and in a warm blanket and hide from the wintry cold. I mean relaxation, as in systems gradually slowing down or losing energy, so essentially exponential decay. Because the generalisation of exponential decay is actually very relevant to many physical systems, some of which do have to do with the conventional idea of relaxation. So now we're going to look at diffusion vs subdiffusion. Now, diffusion you've probably heard before. Diffusion is the statistically driven process where substances, such as, very importantly, water for biological systems, tend to move from regions of higher concentration to lower concentration. Now, this is a statistical trend. It isn't for law, it doesn't have to happen, it just becomes very likely as you increase the number of molecules, and given that, even microscopic, by which I mean, the amount of substances microorganisms deal with, there are still huge numbers of molecules, and therefore diffusion is, in effect, almost inevitable. But we can be a little bit more specific about the diffusion of substances like water, particularly if we're ignoring viscosity, and water isn't a particularly viscous object, at least to a point. And when we're being more specific, we describe the motion of particles using something as a Brownian motion. And Brownian motion played an important role, for example, in allowing the deduction of how many molecules there should be within 1 mole of a substance, so Avogadro's number. So Brownian motion is a very important idea historically. And if you have particles, let's say, which are free to move along a single axis, and you're following Brownian motion, then generally over time you get the average of the square of their position tends to be proportional to time. And I put average because within Brownian motion, objects are moving randomly, so we've got to consider average motion, and we have to square an average because the average itself will be 0. It's the square of the average which is of physical significance. And this idea comes naturally from solving the diffusion equation. Now, Brownian motion in this case, and the diffusion equation, is an example of a Markovian system. And in fact, you know, standard kind of partial differential equations describe Markovian systems, and not just the diffusion equation. And by Markovian, I mean that if we know the state at any moment in time, for example, the present time, and we know the boundary conditions, the spatial arrangement, if you like, of our molecules at that time, then we can predict with absolute confidence how that system will evolve from that point. In short, the system almost has no memory, or behaves like it has no memory of prior states, so states prior to the time we are taking our initial and boundary conditions at. Because we don't need to know any of those prior states to predict its future evolution. We just need the state and boundary conditions at a single moment in time, and then can work out stuff from there. Now, Markovian systems are nice. Not everything is a Markovian system. There are plenty of things with memory. For example, if we're having things like water moving through porous media, or if we're having things like plasma, they have memory, and this is where we get the idea of subdiffusion from. So subdiffusion is like diffusion, but mathematically it's very different because it's diffusion with memory. An example of where we have this is, as I said, through porous material, and there are plenty of synthetic man-made porous material, but the leaf is an example of a porous material, and because within the leaf we have lots of layers, but we have a spongy mesophore, which can kind of hold on to or let kind of gases and maybe water vapor pass kind of through the structure of the leaf, and for example into or out of the palisade cells of a leaf where lots of photosynthesis is happening. So subdiffusion is very common in nature. Porous materials generally are very useful, and plasma is obviously very common in things like stars and other incredibly hot objects. And in such cases, the kind of like fractional version of Brownian motion looks like the average of x to the t all squared is t to the alpha, where alpha isn't necessarily an integer. Alpha could be a fraction. If the system has a memory, alpha will generally be a fraction. And then our differential equation looks like the one above, but we're replacing a integer order partial derivative with a fractional derivative operator. So in this case, the fractional derivative operator we saw previously, the one that involves our wonderful gamma function. Now we've looked at one application, but to finish up, I would love to talk about a particular type of relaxation, which has many applications in physics, including helping humans have good relaxation. So this type of relaxation is called fractional relaxation. And I assure you, this is not a type of ASMR, it's not a type of meditation. This is a genuine, mathematically rigorous process in physics, which will, in firm contrast, this physics might keep you up at night. Albeit that this physics is also helpful for having a good night's sleep when applied to practical matters. So fractional relaxation is, if you like, non-Markovian relaxation. So we mentioned what Markovian is, but what is relaxation? Relaxation is when something's gradually diminishing. So it could be something's gradually cooling. It could be a oscillator is gradually losing energy. It could be, although this isn't really generalizable to fractional relaxation, but in terms of ordinary relaxation, nuclear decay, nuclear radioactive decay would be an example of relaxation. So relaxation is very common in nature, but in a lot of cases we are dealing with continuous processes, and in that case we can consider fractional relaxation versions. But ordinary relaxation follows this kind of differential equation, which has naturally attached to it the idea that the thing that is decaying is following a exponential decay. But, well, firstly, there are many applications of ordinary relaxation. A pendulum gradually losing energy, and as I say, nuclear radioactive decay. Where a nucleus goes from being in a high energy state to a low energy state by emitting some type of ionizing radiation. So ordinary relaxation is quite common, but there are plenty of cases where we're worrying about things relaxing but with memory, so non-Markovian relaxation, and for this we need fractional calculus. The reason we need fractional calculus, or the link between fractional calculus and memory, is something quite technical, which I might do a proper video on at some point. But for now, for introducing the idea of fractional calculus and the importance of the gamma function in it, I am just saying that fractional derivatives relate naturally to systems with memory. Although that kind of makes intuitive sense to a degree, in a very loose sense, because it's like, for example, a half derivative is in between no derivatives, so the function and the derivative of the function. So it's kind of midway between the function and how it's evolving. And so in a vague, fuzzy kind of way, you can see how it has memory, but you can rigorously show it as well. But even just having the equation for fractional relaxation is helpful. So, as I said, if a system has memory, we use fractional calculus, and if we're dealing with a relaxation, we use the fractional relaxation equation, which looks like this. So all we've done is replace an ordinary derivative with a fractional derivative operator. An example of where you might use this is if you're designing a mattress to sleep on, because nowadays there are loads of adverts of mattresses with memory. That is the big thing. We've probably all seen, adverts on TV where somebody is floating mysteriously above a bed, and it's not about some strange form of, supernatural powers. It's just emphasizing how pillow-like and airy and, heavenly this mattress is. And usually those mattresses they have some kind of memory in them. So they might sort of return to something close to their original shape, but they would do so in a way that remembers alterations made to that shape to help, ideally, for a nice sleep. Personally, I always find it bizarre that these adverts feature people levitating above mattresses, because I would struggle to sleep if I was levitating above a mattress, speaking personally. But anyway, there are plenty of applications of fractional relaxation, despite how peculiar some TV adverts may be. So I think here is a perfect place to end this video. So we've talked about the factorial of integers, how to generalize it using the gamma function, and then applications of the gamma function in defining fractional calculus operators. So I hope you've got something from this video, and I really look forward to sharing with you some wonderful physics and mathematics soon. And if you've enjoyed this video, consider checking out other videos on my channel also. But wishing you a brilliant week ahead. And remember, stay curious and keep exploring the wonderful universe.